Game Theory and Learning in AI, and this chapter is competitive games. Today's topic is Bimatrix Games. A Bimatrix game consists of two players or agents, and each agent has a finite set of actions. For each pair of agent actions, there is a payoff, which is a numerical value or just value for each agent. And each agent tries to maximize its payoff. Here's an example. Rock, paper, scissors. There are two agents in this game. Agent 1, who will be colored blue, and Agent 2, always shown in red. The three possible actions available to each agent are rock, paper, and scissors. And the payoffs are +1 for winning the game, -1 for losing the game, and 0 in case of a tie. For instance, when Agent 1 plays rock and Agent 2 plays scissors, then Agent 1 wins because rock wins over scissors, and so Agent 1's payoff is 1. Likewise, when both of them play paper, it's a tie and Agent 1 receives 0 as payoff. For Agent 2, rock and scissors fetches a payoff of -1 because scissors, which is Agent 2's action, loses. Likewise, for scissors and paper, Agent 2's action is paper, which is the losing action, and so again the payoff is -1. We can write down all payoffs in this tabular form. Agent 1's actions are shown in blue and Agent 2's are in red. This is a symmetric game because both players or agents have the same actions and payoffs follow the same patterns. It's a zero-sum game as the sum of payoffs of both agents add up to 0 for all possible joint actions. By the way, I shall refer to action pairs as joint actions. There is no action that an agent can take to maximize its payoff. For instance, if Agent 1 in blue always picks paper, then Agent 2 will pick scissors and always win. Under these circumstances, the best thing to do is for each agent is to pick an action, rock, paper, or scissors with equal probability of 1/3. In other words, the game has no pure Nash equilibrium. This is another game called the prisoner's dilemma problem. Two prisoners, agents 1 and 2, are under interrogation for bank robbery of $10,000 and face up to 10 years jail sentences. They can either cooperate or defect. By cooperate, we mean they confess to the cops, and by defect, they blame the other prisoner of the crime and claim innocence. So their payoffs are the amount of cash they keep minus the length of sentences that they receive. When one prisoner defects, i.e. puts the blame on the other guy, he goes free and keeps half the cash. So his payoff is 5. The other guy who cooperates to the cops, i.e. confesses, gets the 10-year sentence. When both prisoners defect, each gets a 5-year sentence but divides the cash into 5K each. So each player's or each agent's payoff is $5K minus 5 years, which is 0. When both prisoners cooperate, each gets a 2-year sentence but splits the cash into 2 equal halves, so each gets 5K. So the payoff is 5K minus 2 years, which is 3 and 3. At Nash equilibrium, both agents defect. Because if an agent unilaterally switches actions from defect to cooperate, his payoff drops from 0 to -10. If agent 1, for instance, switches from defect to cooperate, his payoff changes from 0 to -10 as shown here. And it's the same situation with agent 2. Hence, neither agent has any incentive to unilaterally deviate from the Nash equilibrium. This game has a unique Nash equilibrium where both agents pick the same action, defect. Why is both cooperating not a Nash equilibrium? After all, each agent would get a payoff of 3 when both cooperate, right? And that's higher than the payoffs of 0 at Nash equilibrium. Here's why. Suppose agent 1 unilaterally switches from cooperate to defect. He increases his payoff from 3 to 5 as shown here. Likewise, agent 2 switching again unilaterally from cooperate to defect increases his payoff from 3 to 5. So both agents cooperating is not stable. It's not a Nash equilibrium. This is another example called the hawk-dove game. There is food worth a total payoff of 10. Each agent can choose to play hawk or dove. A hawk fights for the food. A dove gives up and goes without food. Now the penalty for fighting is -2. When both agents are hawks, they fight for the food, receiving a penalty of -2 each. But they get to divide up the food, which has a value of 10. So when divided by 2, it's 5. 5 minus 2 is 3. So each agent gets a payoff of 3. On the other hand, when both agents are doves, they peacefully divide up the food so that each's payoff is 5. There is no fighting, so no penalty incurred. At Nash equilibrium, both agents are hawks. Unilaterally deviating from hawk to dove would result in a payoff drop from 3 to 0. 3 to 0 for agent 2 or 3 to 0 for agent 1. This is yet another example. Here, the two agents are spouses. The husband prefers to go to the soccer game, which has a payoff of 4 for him, and the wife prefers to go to the concert, which has a payoff of 3 for her. Now, if they're together, there is an additional payoff of 5 each. So if both attend the concert, for example, the husband doesn't like the concert, but due to the presence of the wife, since he's together with his wife, he gets a payoff of 5 nevertheless, and the wife gets a payoff of 3 for being at the concert, plus 5 for being with her spouse. There are two Nash equilibria for this game which are shown. Here is a generic Bimatrix game with two different sets of actions. Agent 1's actions are A, B, C, D, and Agent 2's actions are P, Q, R, S, and T. Now, Agent 1 looks only at its own payoffs. It has no knowledge of Agent 2's payoffs. And this is Agent 2's view. Agent 2 likewise has no knowledge of Agent 1's payoff. It only chooses to maximize its own payoff. Now, a great joint action would be BQ because that would result in payoffs of 7 and 8 for the agents, and the total is 15, which is very high, and 7 and 8 individually are quite high payoffs. Unfortunately, this 7-8 is not at Nash equilibrium. Here's why. Now consider agent 1 whose action is B and the payoff is 7. If it unilaterally deviates from B to D, the payoff increases from 7 to 8. So agent 1 has no incentive to stick to this action B. Likewise, agent 2 has no incentive to stick to action Q because its payoff would change from 8 to 9 if it unilaterally deviates to from action Q to action S. This game has two Nash equilibrium points. Now let's look at why agent 1, the blue agent, will not deviate from the Nash equilibrium points 4 and 6. Because we have to look at the payoffs if the agent unilaterally switches actions. Suppose this is the Nash equilibrium point, then agent 1 is selecting action C, and if he deviates to B or A or D, then the payoffs will go from 4 to 1, 2, or 3, all of which are lower than 4. Therefore, this agent has no incentive to deviate from this Nash equilibrium point. In a similar manner, this payoff 6 for the blue agent, agent 1, is the highest in this column. Therefore, this is a Nash equilibrium point. From the agent 2's view, again, these two are Nash equilibrium. If agent 2 unilaterally deviates from, say, T in this Nash equilibrium to any other action, then the payoff decreases from 4 to 0, 1, 2, or 3, which are all lower. Likewise, in this row, 5 is the highest payoff for agent 2. Neither agent has any incentive to unilaterally deviate from these two Nash equilibrium points. Now let's look at the formal definition of a normal form game. A bimatrix game is, in fact, a special case of a normal form game with two agents. Definition. A normal form game or a static game is a three-tuple consisting of a set of agents n with cardinality n and action sets ai for each agent I and payoff pi I of each agent I, which is a mapping from the joint action space to a real number. And lowercase ai is any action of the ith agent, and A is any joint action of all the n agents. Now, this notation is peculiar to game theory. Script A sub negative I is the joint action space of all agents excluding agent I. That's why I have this subscript negative I. Agent I's action isn't present. This is any joint action of all the agents excluding agent I. And A is the joint action space which includes agent I, and we can denote this as AI comma A negative I. Now this is a bimatrix game with two agents whose action spaces are A, B, C, D and P, Q, R, S, and T. Now we can represent the payoffs of the two agents as these two matrices here, P1 and P2. P1 consists of the payoffs of agent 1, which are 1, 1, 2, 1, 0, 1, 7, 1, and so on, all the way to the last one, which is 6. And likewise, P2 consists of the payoffs of the other agent, agent 2, 1, 1, 5, 1, 1, 5, all the way to 4, the last one. Now, actions can be represented as vectors. Let's see, consider this joint action A. Agent 1's action is B and agent 2's action is S. B and S. So agent 1's action A1 can be represented as a 4 by 1 vector. Why 4? Because agent 1 has 4 possible actions available, and it contains all zeros except at position 2, because the second action is the one that is being played by agent 1. Likewise, consider agent 2. Its action can be represented as a 5-dimensional vector because there are 5 possible actions, and since agent 2 picked S, the fourth action, we have a 1 in the fourth place here. We can easily compute the payoffs of agents 1 and 2 using the two payoff matrices, P1 and P2, and these vectors of actions, which are E2 and E4, because it's E2 because we have a 1 in the second position here, and this is E4 because we have a 1 in the fourth position. And these are equivalent to A1 and A2. So pi 1 A is BS, is equal to E2 transpose P1, because we are looking at agent 1, times E4, which is equal to 5. Likewise, payoff pi 2 of A, agent 2's payoff, is E2 transpose P2 here, because we are looking at agent 2 now, times E4, which is 8. So we can compute the payoffs from these vectors of actions and the payoff matrices. Dominance is a relationship between two pairs of actions of the same agent. We consider agent I. So this action AI dominates another action A prime I, written in this manner: AI dominates A prime I if and only if for all A negative I, that is, all possible joint actions of the remaining agents except agent I, the payoff of agent I when it plays AI is always greater than equal to the payoff when it plays A prime I. So AI always gets a higher payoff than A prime I, regardless of what all the opposing agents are playing. Only in that case, AI dominates A prime I. Furthermore, action AI strictly dominates action A prime I if and only if, in addition to dominating AI prime, for there exists some action A negative I of the other agents such that the payoff of agent I when playing AI is strictly more than when playing action A prime I. Now consider this example here where agent 2 has these four actions and we shall compare action P with action Q. Now regardless of what agent 1's action is, we can see that when playing P, agent 2's payoff is more than when playing Q. Here's why. Now, when agent 1 plays A, B, C, the corresponding payoffs of agent 2, if it plays P, are 3, -1, and 3, 3, -1, and 3, and when playing Q are 0, -2, and 0. 0, -2, and 0. And element-wise, we can see that 3, -1, 3 is strictly greater than 0, -2, 0. Whence we conclude that P strictly dominates Q. Likewise, if we compare P and S, these two actions, the payoffs when playing P are 3, -1, and 3, and when playing S are -2, -3, and 1. And again, element-wise, we can see that this is strictly greater than this, whence action P strictly dominates action S. In fact, we can simplify games using this dominance. Here's how we simplify. Since we now know that Q and S are being dominated by P, this agent 2 is never going to pick these two actions, Q and S. They are redundant, and hence we can completely eliminate these two actions and simplify the game. Recap. So we looked at normal form or static games, which is a three-tuple of agents, actions, A sub I of each agent, and payoffs, pi sub I of each agent. Nash equilibrium is when no agent will unilaterally deviate. And we looked at bimatrix games, which are between two agents, and the payoffs are represented as matrices. Then we looked at dominance. Now here's a question to test your knowledge. Can you find any pure Nash equilibrium in this bimatrix game? Thank you.